Okay, so hi, my name is Vinicius da Rocha. I am a PhD student at LCN, Laboratório Computacional de Materiais at UFSM. So today I will present the seminar entitled A Bird Eye View of Density Functional Theory. Um, so when we are going to do a simulation, we must take into account the size of our system shows the most efficient method to handle all the problems involved. Well, this picture shows the different methods associated with the different systems as a function of their size. So to solve quantum problems, we need to use methods based on or statistical models or on first principles in quantum mechanics, which can greatly increase the computational cost of your simulation. So DFT is a method that uses certain approaches and techniques that allow us to use the theory of quantum mechanics in its purest possible form, let's put it that way. So to solve a problem in quantum mechanics, we must solve the many-body Schrödinger equation. Here, already in its time-independent form. Uh, the system Hamiltonian is given in this form, where the first and second terms correspond to the kinetic energy of electrons and nuclei, and the other terms refer to Coulomb interaction energy. Well, solving this equation for many bodies is a very difficult task. One of the ways to simplify this problem is simplify the Hamiltonian. So now we make your first approximation, the Born-Oppenheimer approximation. Here we consider that electrons move much faster than nuclei. Therefore, electrons change position almost instantly in response to changes in the position of nuclei. So, without laws of generality, we can consider that the nuclei are stationary and act as an external potential. So the second term of Hamiltonian is null and the last term is constant. So our Hamiltonian can be written in a simpler way and becomes the electronic Hamiltonian. Even with this simplification, the Schrödinger equation is impossible to solve for a system that's not a hydrogenoid system. The wave function is a function of three n variables. That is, three variables for each electron. So, for example, the CO2 molecule, we have a 66-dimensional problem. And for example, for a gold nanocluster with 111 gold atoms, we have a problem of 26,307 dimensions. So, therefore, a tip to solve a problem of this type is to replace the wave function by another variable that is as significant as it. So DFT comes with the proposal that this variable can be the electronic density. Previous work by Thomas Fermi already showed that electron density could be used to resolve a gas with free electrons. So the electronic density is a function of three variables and it has a direct physical interpretation. The wave function can be written as a Slater determinant, as we know have instead of a many body problem, several single electron problems. What we will have. So the question now is whether by making this switch, we are able to arrive at the correct properties of the materials. So Homberg-Kohn in 64 published a work presenting the so-called Hohenberg and Kohn theorems, where they show that it is possible to change the wave function by electron density and still have the correct energy of ground states. So the first theorem says that the energy of the ground state is a unique functional of electronic density. So to prove this theorem, we propose two Hamiltons with an external potential that carries at the same electronic density. So the expected value of energy for the system arrives at an absurdity, which proves that the ground state energy must be a unique density functional. The second theorem says that the electron density that minimizes the energy of the density functional is the true ground state density. Thus, the ground state energy can be written as a density functional, where the Coulomb interaction depends on the system, and the terms of electronic exchange and correlation have a universal validity. These two terms are called the Hohenberg-Kohn functional. So this exchange and correlation functional is not null, and perhaps this is the biggest problem with DFT. So we have to use approximations to describe these terms. There are different types of approximations depending on the student system. For example, local density approximations only take into account the electron density at the point, and generalized gradient approximations also take account the electron density gradient. There are some types of potential in the literature that use these approaches. Here we have Better-Sleep potential, PBE potential. For example, the B3 leap functional is a hybrid functional. So for the construction of this potential, use a combination of the GGA and LDA functionals plus the exact exchange term of Hartree-Fock. In this work, for example, the authors show that the percentage difference for various functionals in the band energy calculations compared to the experimental. So the theorems shown in the previous sections do not give an exact expression for energy as a density function. Not to show how to find the shape of these densities. Therefore, it remains to determine an analytical expression for each of the terms of the energy functional in terms of the electron density. So in 65, Kohn and Chan introduced the use of the concept of an independent particle frame of reference. The idea is to replace the original main electron
Two
problem
minutes.
with no interacting electron problem, assuming that the ground state density of the original interacting system is equal to that of the non-interacting system. So we use the variational principle to minimize the energy functional in relation to density, and we arrive to a Schrödinger type equation. This equation must be solved in a self-consistent way. We enter an initial electron density, calculate our external potential, and solve the constant equations. If the new density is within a convergence criterion, the process ends and we can obtain the properties of our system as forces, energy. To buy the constant orbitals, we must use predetermined base functionals. So an example of functionals is the 6 minus 3 1G star that it's called double zeta because it splits the valence layer into two parts. The larger our base functional is, the more degrees of freedom our system electrons will have, but our computational cost will be greater. So just to be clear, DFT is a theory for ground state only. To study excited states, we must use its time-dependent extension. And linear response theory, using linear response theory, we were able to obtain the excitation energies and their vibration frequencies. There are several types of codes that implement DFT and its extensions. extensions. Quantum Express and Orc are open source codes. In my master, use Gaussian 09 most of the time. Here we have some applications of DFT. We have photodynamics therapy. We have two applications in characterization of materials and structure and band energy calculations, and also is used nowadays to characterization of materials used in generation and storage energy. Thank you. That's all.